far as where we're headed from here, one of the things I like to do whenever we move on from an exam is to take a look at where we've been and where we're heading. And so opening up the syllabus here and going down to our calendar, and here's those problems in case you've forgotten, the representative ones you should be working on. For our next exam, we have it scheduled for October 11th, and that exam is going to cover the last half of Chapter 12 and Chapters 13 and 14. This semester has one fewer class meeting day than any other one that I've taught this portion before. So we've kind of squeezed. If you felt a little squeeze here for the first exam, that's probably the case. If you feel a little squeeze for the second exam in terms of time, you'll feel it for the second exam. And so I've kind of tried to squeeze a half day out for each one of those. And so the pace then from the end of the course on, from Chapter 15 on, should be kind of normal, what I would do in a normal course in terms of pace. As far as labs go, we do have our classroom visits this week. All of our classroom visits are going to be done at Wilson Elementary. Wilson Elementary borders Andover Oak Grove. If you go up Round Lake Boulevard, you'll find it kind of near turnoff by the McDonald's up there on Round Lake Boulevard. And probably about a 10 to 15 minute drive from here.
Andover, Anoka, not Andover, Oak Grove.
Oh, that's where I live, Andover, Oak Grove. So it's Andover, Anoka, yes. The other thing is, if you are in the Thursday lab, I did send you an email over the weekend, I think. Did I? Didn't you get it? Okay. And so for the Thursday afternoon people, they have something else that is going on like at 3 o'clock for those fifth graders. And so they would really, really like if you guys could show up earlier, even if you get there at 2:30, that would be helpful, and then they wouldn't feel so rushed. And if you could be ready to go by 2:30, they would appreciate that. If you are able to do that, please let your lab professor, Dr. Lutz, know so that he can get your time scheduled with them. So, any questions about the visits or the exams in general? All right. Now, if there is some hope, here's the hope. I know that there's many of you that talked about your math credentials coming in here, and boy, I've been up through multivariable already, and I really want to do some math stuff. If it's math stuff that you like, that's where we're headed. And if you don't like math stuff or whatever, it's been a while, that's all right. The math doesn't require calculus in here, but it does require higher level algebra than, say, your Chem 1 experience did. We'll be doing a lot of things where we work with log functions, natural log functions, anti-log functions, exponential functions. The variables with which we work it can be a little bit more complex with equations to work with, but if you've had up through whatever the 2 years worth of high school algebra or our 250, or 250 I think it is here, you should have a math background adequate for it, but we do recommend that you've had the college algebra, which I believe just about everybody in here has had. So we are headed into more math stuff, and you'll see that the next several exams are going to be more emphasized on calculations. One last comment on the test is, if you want to kind of get it inside my head, and I know that there's a couple of you that have had me before, but when I think about designing exams, here's what I think. I think 25% of your questions should be what I consider to be easy, 25% of them should be considered difficult, and the middle 50% should be somewhere in the middle. So that's kind of where I think of it. And unfortunately, there were some of you that, like the back page problem, that was a give me points. Okay, if you're missing percentages at this stage, and maybe you were shocked that it was just that simple. I know some of you were thinking it's going to be really hard, and it wasn't. And so, just like I say, if you want to get in my head, when I always think about 25%, I consider easy. 25% I consider difficult, and there'll be middle 50%. So if you hadn't seen the simple stuff yet, that last one was supposed to be the simple one on this test, and it was. So that said, today what we're going to do is we're going to begin work on colligative properties of solutions. And as far as colligative properties of solutions go, we define colligative properties of solutions like this. We say that these are properties that depend only on the solute particle concentration and not on their identity. So in other words, whatever we observe for colligative properties, it doesn't matter what we have dissolved, all of them behave in a similar manner. It's just something that depends upon whatever the concentration is of the particles in the solution. Now, you observed a couple of these in your first semester if you took your Chem 1 here on the Cambridge campus. You might remember a lab where you learned how to use the vernier probes, and there's one where you took some salt and you added it to a mixture of ice and water. And what happens when you mix salt with a mixture of ice and water? What happens to the temperature? Go up or go down? Goes down, exactly. If you've made ice cream at home, you know that as well. And we call that phenomenon freezing point depression. And if we were to add a solute to some water and bring it to boil, what happens to the boiling point? Boiling point goes up, exactly. And we call that one boiling point elevation. So those are the two of them. If you took your Chem 1 here at Anoka Ramsey, whether on the Cambridge campus or the Coon Rapids campus, you would have looked at these already. And then there's a couple others that you didn't do. One is called vapor pressure depression. And the fourth is called osmotic pressure elevation. Now, these two here, the boiling point elevation and the vapor pressure depression, these are observed only when we have non-volatile solutes. And what does it mean if we say that a solute is non-volatile? Yes, Joe?
It does not tend to vaporize at room temperature.
Exactly. At least not vaporize well. Everything will vaporize, but it just means that it won't vaporize well at all. So again, the solutes for boiling point elevation and vapor pressure depression should not evaporate easily. Now, as far as what they depend on, we look at these first two. We say that these two here depend on the molality. That's one of the reasons why we learn about molality. And I think some of you on that back page read it wrong. You read it as molarity and not molality. So again, these properties depend upon the molality of the solution. Vapor pressure depression this here depends on the mole fraction. And then the last one, the osmotic pressure, this one here depends on the molarity. So again, there's a reason why we spend time looking at the different concentration units and converting between them because each one of these depends upon a different concentration unit. And so again, when we talk about colligative properties, it doesn't matter what the solute is. Whatever we observe for salt should be observed for sugar. Whatever we observe for sugar should be observed for alcohol, like ethanol, not for all of them, but which ones? Because ethanol would be volatile, so if ethanol was added to water, it would only affect which ones? 1 and 4, exactly. And that's, again, because ethanol, alcohols, tend to be volatile materials. So again, whatever we observe for one solute should be observed for all of them. Now there's some mathematics associated with these, and so here we are getting back into our math now finally. Here's some equations. I'm going to write down 4 of them. And first one here, delta T sub F is equal to M times K sub F. We have delta T sub B is equal to M times K sub B. Over here, we will have delta T sub F is equal to I times M times K sub F. And we'll have delta T sub B is equal to I times M times K sub B. Now we need to define what these things all stand for. And we'll start with this one right here. This here is called the freezing point depression. Delta T sub F is called the freezing point depression. And delta T sub B is called the boiling point elevation. Basically, it will tell us, the delta T sub F will tell us how much the freezing point will go, which direction? How much it will go down, and the delta T sub B will tell us how much the boiling point will go up. So it doesn't tell us the actual boiling point. In order to find the actual boiling point, we'll have to take each one of these and either, in the case of the boiling point, we'd have to add it on to the actual boiling point. In the case of the freezing point depression, we'd have to subtract it from the actual freezing point to find the freezing point of the solution. M, in all cases, stands for the molality. M stands for the molality of the solution, not the molarity, but the molality of the solution. And K sub F, this stands for the freezing point depression constant. These here would be the freezing point depression constant. And the delta T sub B, the K sub B, these are what we call the boiling point elevation constant. Now, I suppose my book is, do I have this working here yet? All right, my book is still going. So now, in terms of where you'll find information for this in your text, I'm looking on page 503. And then, have any of you noticed that the pages are sometimes off on this electronic book? They are. It's annoying. So where you're going to find this is, I'm seeing a table here on the bottom of page 503, which shows the freezing point and the freezing point depression constants and boiling point elevation constants for these substances. And so when we talk about these, please note that these are solvents. And each solvent has its own freezing point depression constant. Each solvent has its own boiling point elevation constant. In order to do these calculations, you'll need to have these provided. It's not something you need to memorize, but it'd be something that you'd be provided because, again, each substance has its own specific value that you'd wind up using. And then if we go back to, I think the only thing we haven't defined yet is the letter I. And the letter I is what we call the Van Hoff factor. I is called a Van Hoff factor. And the Van Hoff factor, and I think I misspelled it, there's an apostrophe in here somewhere, but it doesn't matter. The Van Hoff factor is something that will depend upon the number of ions formed in the solution. And so when we look at these formulas, the reason why they look almost identical and why these include the letter I is because these here on the right-hand side, these are for ionic solutes. So again, these here are used for ionic solutes. And that should be pretty apparent, or it would be helpful if we look at it, the letter I. I doesn't stand for ionic, but if it helps you to memorize it, I is the Van Hoff factor, and it's used in ionic whenever we have an ionic solute. And basically it comes down to the Van Hoff factor is a theoretical value that we can look at that depends upon the number of ions that form when we place something into solution. So for example, if we put something like sodium chloride into water, how many ions will form when we put sodium chloride into water? 2. And those ions are Na plus and Cl minus. Exactly. And so in a case like this, we'd say that the Van Hoff factor, the I value, is equal to 2. And if we had something like this solution, calcium nitrate, how many ions will form? What would the I value be for calcium nitrate? I hear 3. Do I hear anything else? How about 9? Is it 3 or 9? Well, let's go back. Which ions are present here? Calcium. How many calcium ions? Okay, and what other ions are present?
6 O's and 2.
Be careful. This is where the terminology is important. What's the other ion that's present in here? You were right the first time. Which ions? Nitrate. What's the formula of nitrate ion? NO3 with a charge of 1 negative. And how many nitrate ions are there? 2. Exactly. So calcium nitrate is composed of 3 ions. It's 1 calcium ion and 2 nitrate ions. So the I value in this case is going to be equal to how much? 3. Yeah. And again, it's 3 because 1 mole of calcium nitrate yields 3 ions altogether. Now, if we think about it, this should make sense because the way we define colligative properties is these are properties of solutions that depend only on the solute particle concentration and not on their identity. So if we put a molecular substance in there like sugar, sugar has a chemical formula, if we're talking about sucrose sugar, has a chemical formula of C12H22O11. It's a big molecule, but again, it's a molecular compound. And if we put a molecular compound into water, what happens to molecules? Do they break apart or do they stay together? They stay together. The sucrose molecules stay whole. They don't break apart into individual atoms or ions. The sucrose molecules stay together. And that's true for all molecular substances. Well, we'll find out that's not true once we get to acids and bases, but for now it's true that if it's a molecular compound, it's going to stay whole or intact, and we don't need a reason to say that the I value is equal to 1, because in all cases, molecules are going to stay together. But in ionic compounds, if we have something like sodium chloride again, it doesn't stay in solution as sodium chloride. It's in solution as sodium ions and chloride ions. So 1 mole of sodium chloride is going to produce 2 moles of particles. Okay? And 1 mole of calcium nitrate is going to form how many moles of particles? 3 moles of particles, exactly. They'll form 3 moles of particles, which we've identified here by this Van Hoff factor of 3. Now, the reality is that these are theoretical values. So when you talk about the Van Hoff factor, that is a theoretical value, and that assumes that every single unit of sodium chloride dissociates and does no longer interact with each other. It assumes that in the calcium nitrate that all of the ions will dissociate from each other and will be taken on by water molecules. The reality is that in the solution, what will happen is that sometimes, well, first of all, when we look at this, this represents sodium chloride. The green ones here are the chloride ions. The purple ones here are the sodium ions. And ordinarily, what will happen is that they will be totally separate entities and they won't interact. But occasionally, what will happen is because these here have opposite charges, even though they are surrounded by water molecules, sometimes they will interact with each other and hold on to each other. If they're holding on to each other, this kind of as a group then is acting as one particle. Okay, as a result then, something like sodium chloride actually won't observe that Van Hoff factor value of 2. It's actually going to be something a little bit less than 2. And what this table represents, and this is also in your text, this is a figure that appears on page 507. This is just telling us that sometimes those ions will still interact and hold on to each other and will not be measured as a separate entity. And that is something that will vary depending upon the concentration of the solution. So you'll see here that this is given for a 0.05 mole concentration for the solution. And typically as the concentration goes down, as the solutions become more dilute, then it is more likely for them to be present as separate entities. And the more dilute it becomes, the closer these Van Hoff factors get to their theoretical values. As the solution becomes more concentrated, you have a whole bunch of sodium ions, chloride ions, in this case here, all together. It's going to be more likely for them to interact and hold on to each other. And so the more concentrated it becomes, the more this actual measured Van Hoff factor is determined. That value actually begins to decrease the more concentrated it becomes. Jason?
So we're we should just use the expected value?
When we don't know otherwise, we start with the expected value. And what we often do actually is if we're working with solutions, we actually will start with the concentration of observed boiling point, and then we'll work backwards to determine what this Van Hoff factor is. So that's the way it's usually implied or applied, is we work backwards to find out what it is because we want to know what degree of interaction is there between the particles. So that's the way scientists usually use it, is to find out what that degree of interaction is between the particles. So we work backwards from the actual observations to find that factor. Okay, anybody else? All right, so what we're going to do here then is we're going to look at some sample calculations, and we're going to start by these two here. We are going to calculate the theoretical freezing point and boiling point of solutions prepared by dissolving the following amounts into 250 grams of H2O. And I'm putting a decimal after the 250 to indicate that we have 3 significant figures. So for the first one, A, we're going to use 50.0 grams of this stuff. And anybody recognize what this stuff is? You mentioned it already today. What is it? It's sugar. Specifically, which type of sugar? Sucrose sugar. Okay, because we have like glucose sugar, fructose, but this here is sucrose sugar. And then the other one's going to be 50.0 grams of sodium chloride, which of course is which stuff? Salt. Right, so basically we're comparing what you would have at home, sugar and salt. You have a bag of sugar, a bag of salt, and we want to throw some of this stuff out on the driveway, on the sidewalk, to get our ice to melt. And we want to know which one's going to be more effective at it.
Wouldn't that be salt, not sugar?
Oh, yeah, I don't know why I wrote that. Just like Andover Oak Grove, right? It's Andover, Anoka, so. Okay, so to do these, we go back to our formulas, which we have on the previous page. Which one of these two is going to use the Van Hoff factor equation? All right, the salt will, because that's the ionic compound. So let's start here, first of all, with the sugar. And the sugar, we have delta T sub F. In fact, if you really want, you won't even need to use the two different forms. If you want, you can always use this same equation and realize that the Van Hoff factor in all molecular solutions is always going to be equal to 1. So if it's easier just to keep in mind the one equation, you can go ahead and do so. So for sugar, we will plug in the values. Value for I then for sugar, of course, is 1. And then we'd look up the freezing point depression constant, which in our text is on page 503. And which substance are we going to look up the freezing point depression constant for? Is it for water or for sugar? For water, because their constants are for the solvent, not for the solute. And we see in the case of water that that value is equal to 1.86. And the units on here are degrees Celsius per molal. Well, I guess I switched the order, but that's okay. It's the same variables. And then we're going to multiply it by M, which again is called the molality. So let's go ahead and figure out what that molality is of the solution. We have 50.0 grams of the sucrose, which is C12H22O11, and we need to wind up with units of moles of the sucrose per kilogram of the H2O. And so right now we have grams of this over 250 grams of H2O. And we need to get over to these units over here. So let's go ahead and do some magic with these. And the magic we need, I'm going to slide these down here just a bit. We need to convert our grams of the sucrose to what? To moles. And so in order to convert grams to moles, what do we need? Molar mass. So where does the molar mass go? On the bottom. Anybody have that molar mass yet? If you need it, grab your periodic tables. Anybody needs a periodic table? I have some. Anybody need a new periodic table? Anybody need a new periodic table? All right, let's get that molar mass figured out here, please. How much?
332.2.
Oh, I think we're off.
Sorry.
342. Yeah. Point. like 0.3, right? All right, then this is going to be for every 1 mole of C12H22O11. Anything else we need to do with the numerator now? No, we're good. So now what do we need to do? Convert grams of water into kilograms of water. So to convert grams into kilograms, grams of H2O up above, kilograms of H2O down below. And what is the conversion? On top we put in 1,000. On the bottom, 1. Good. Grams of H2O cancel out. And I left my calculator in my office. That's why I carry extras. Okay, so we'll take 50, divide it by 250, multiply it by 1,000, and divide it by 342.3. And I think I did something wrong. What are we coming up with? Oh, I must have, yeah, I think I must have only multiplied by 100. My excuse is this is not my calculator. There it is. That looks better. Okay, so I'm winding up with 0.584. And of course, this here also translates to units of what? Molal, exactly. So we'd say that this is equal to a 0.584 molal solution. So we can then take the molality and plug that in up here, which was the 0.584 molal. Once you plug it in there, what happens to the molality? Cancels out. So we'll take 1.86, multiply that by 0.584, and we wind up with an answer of, and I have 1.0, how many sig figs do we need? 3. So I wind up with an answer of 1.09, is that right? Okay. And then the units on this would be 3 Celsius. Now, this is not the freezing point of the solution. What do we do once we get this value? Subtract it from the freezing point of water, which is 0.00. In case you didn't know it, it's in the table there for you. Okay, so freezing point is going to be equal to 0.00 minus 1.09, and we wind up with an answer of negative 1.09 degrees Celsius. Any questions on this? Okay, now we're not going to do all of these here. We'll just do a few of them, maybe a couple of them, just so we have it. Let's do a comparison here for the freezing point of the sodium chloride, which of course is letter B. In letter B, we had 50 grams of sodium chloride. So we'll take the 50.0 grams of NaCl. And of course, this here we were also putting into water. So we're dividing it by how much? 250 grams of the water. Now, like before, we're going to convert this over to molality. We need to first convert grams of sodium chloride over to moles. So to convert grams to moles, this should be an easier conversion. You have your periodic table handy. 22.99 plus 35.45 gives us 58.44. These units are going to cancel. And from here, next step is going to be to convert grams of H2O over to
Kilograms.
kilograms. So same conversions as before, 1,000 grams of H2O for every 1 kilogram of H2O. Grams of H2O are going to cancel. Once we have this in here, we then multiply this through. We'll take 50, divide it by 250, multiply it by 1,000, and divide it by 58.44. And we wind up with a molality of 3.42. And the label here then is going to be molal, and it's molal of sodium chloride. So now that we know that's molality, then we go to our freezing point depression equation, which is I times K sub F times the molality. We then plug in our values, and like Jason asked earlier, what do we do about I? So in this case, we don't know for sure, so we'd assume the I value is going to be 2. Okay. We realize it's probably a little bit less than 2, but we don't know for sure. When we don't know for sure, we use a theoretical value and realize this will be an approximation. K sub F is going to be 1.86. Units there are degrees Celsius per molal, and then we multiply it by the molality, which is 3.42 molal. Molality cancels out. We then take 2 times 1.86 times 3.42, and I cannot operate my calculator apparently. 2 times 1.86 times. What are we coming up with?
12.7.
12.7. There we go. And that's going to be 12.7 degrees Celsius. Now, of course, this is not the freezing point. What do we need to do to find the freezing point? Subtract from 0. So the freezing point in this case is going to be a negative 12.7 degrees Celsius. So there is a reason why we put salt on the sidewalks and highways rather than sugar. And why is there a couple reasons why salt is so much more effective? 2 reasons.
Small molar mass.
Small molar mass and?
Ionic compound.
That's an ionic compound, exactly. Those are the 2 factors that work for it. And in Minnesota here, if it gets really cold and the roads are icy, we don't even put on sodium chloride. You know what we put on? We put on calcium chloride. We spray it down. And why do we use calcium chloride? Van Hoff factor is 3. Because the formula for calcium chloride is CaCl2. And there's 2 chloride ions and 1 calcium ion for each unit of the calcium chloride. So in Minnesota here, we do experiment with that stuff. It isn't straight salt. If you see the salting truck in front of you, the sanding truck, or whatever, they are putting down sodium chloride on there. But if you see them spraying, usually it's going to be some mixture of sodium chloride or calcium chloride, and sometimes, if it's really cold, it could be straight calcium chloride that is being applied. Yes?
Would the I value be given to us, or do we have to figure it out?
You need to figure out the I value. But if you know the formulas for the ionic compounds, you should be able to figure it out. Just don't get tricked on it. I mean, I know you had the right answer there to begin with, but don't get tricked on it by the formula. You do need to know that that's a polyatomic ion in there, and you would need to know how they separate. Okay, anybody else? Okay, now if we were to do the boiling point elevation, I guess we don't have to do a whole lot of extra calculation to get the boiling point elevation on. Let's just do a quick one for the salt. We won't do them both for the salt and sugar. But let's, for the salt, do the boiling point. And for the boiling point, delta T sub F, this would be delta T sub B is equal to I times K sub B times the molality. So the I factor is still equal to 2. Case of B now, we'd have to look up, which in the case of water is going to be 0.512. And that's going to be degrees Celsius per molal. And we already calculated the molality of the water is 3.42, and that is molal. So your molality is going to cancel out. We multiply these through. We get 2 times 0.512 times 3.42, and wind up with an answer of 3.50. The label on this will be degrees Celsius. Now if we want to find the boiling point of water, what do we need to do? Add it to the boiling point of water, which we really only have out to the 10th place, and so the boiling point is given as 100.0 degrees Celsius. So add on to that 3.50 degrees Celsius, and following our rules for rounding for addition, it'll tell us our answer should be 103.5. The label, degrees Celsius. Okay, and for any of you that think that the reason why you add salt to a pot of water, like when you're cooking pasta, is to make it boil faster or higher, that's just a wives' tale. It doesn't do that at all, because if you look at what this calculation is, this is 50 grams of salt and 250 grams of water. How concentrated is that going to be? I don't think any of us drink salt water that concentrated, do we? So, and that's only raising the boiling point by 3.5 degrees Celsius. So a pinch of salt in a pot of water isn't going to do anything. Okay, so save your pinch, and again, you don't need it because even a tiny pinch won't do anything to the boiling point. All right, any questions? All right, next up then, we are not going to look at vapor pressure depression here. I will promise you that there will not be any vapor pressure depression questions on your exam, so you can say that he said so, and you have my recording. It's going to be in D2L anyhow, so I'm promising you that there will not be any on your exam. If there are some in your homework, you're accountable for those, but exam-wise, there will not be any. So where we're going to wrap up then for chapter 12 is by taking a look at osmotic pressure and osmosis. Now, I remember as a student where I learned about osmosis, and it wasn't in chemistry, it was in biology. And the way that the biologists defined it was very confusing, because we'll start kind of like how they do. They talk about it as being the movement of water through a semi-permeable membrane from areas of, and here's how the biologists defined it. This is how I remember learning it. They don't write this down because I don't think it's a good way to do it. It says the movement of water through a semi-permeable membrane from areas of higher concentration to areas of lower concentration. Sound familiar? Okay, that's the way I learned it. What's not good about that is that when they talk about the concentration that way, they're talking about the concentration of water. They're not talking about the concentration of solutes. When chemists talk about concentration, we're not talking about the concentration of the solvent. We always talk about the concentration of the solute. So when a chemist defines it, we talk about it as a movement of water through a semi-permeable membrane from areas of low solute concentration to areas of high solute concentration. And so again, we always talk about it in terms of solute when we're in chemistry. And one of the figures here shows about how osmosis and osmotic pressure works. In this particular one, we're starting with some pure water on this side, and we're starting with some impure water on this side. So you can consider this to be like your deionized water. This over here would be like your tap water. And then dividing them is a semi-permeable membrane. Now, first off, we talk about what a membrane is. A membrane is basically something that is really, really thin. Okay? Membrane could be something like a cell membrane of one of your cells. Membrane could be something like that holds the egg yolk inside of the actual yolk itself. So if you break that membrane, then you'll see the egg yolk beginning to move out. So that's what we consider to be a membrane. If it's semi-permeable, what does it mean, first of all, if we say something is permeable? Something that's permeable means it allows things to pass through. Okay? And if it's semi-permeable, that means it allows some things to pass, but not everything. Okay, so a semi-permeable membrane is a very thin piece of tissue often, or it can be an artificial means, very thin, that allows some things to pass through and not others. So what will happen then is that because the solute is more concentrated over here, the water is going to move in which direction? Right, the water is going to move through this way. And it's going to move through there until what happens is that this level of the liquid is going to go up. And it'll eventually stop moving up because this now, that's higher on this side of the tube, is going to begin exerting a pressure. If you just had water in a U-tube like this, what would happen is that the water on the two sides would be equal. But as that starts moving up here, this side is going to begin acquiring a higher pressure, and that then is going to begin pushing backwards against the movement of the water. And so what happens is if you measure this difference in height between the two, you wind up calculating what is called the osmotic pressure. And so when you think of pressure, always think of pressure being something like a push. If we put something like a block of wood or this container on the surface, it is exerting a pressure onto the surface of the table. So likewise with the water, the osmotic pressure you would think of as being a push of the water on that direction against the solute. And then again, ultimately to measure that osmotic pressure, you can use that semi-permeable membrane to measure this difference in height. Now, there's a couple interesting things you can do with this in ways that you can apply it. One of the ways, and this is kind of an interesting little thing, this is something that if you've never done this before, I'd recommend that you go home tonight and try it. And here's what you need to do it. First of all, this is going to be something that would take 3 days, but each day would only take about 5 minutes of your time. In day one, here's what you do. Take a cup, and into that cup you're going to place some vinegar. And if you took 1020, this was an extra credit lab we did in 1020. Have any of you done this one with an egg and vinegar before? Okay, a few of you have done it. So in the first day, put some vinegar in a cup, and then inside the cup you're going to place an egg. That egg is going to be in its shell. It's going to be a raw egg. It's not going to be a hard-boiled egg, but it's going to be a raw egg in its shell. So raw egg in the shell. Now what do you suppose the vinegar is going to do to that raw egg in the shell? Shell is made up of calcium carbonate. And this is vinegar, which is an acid. So what does an acid do to carbonates? Breaks them down and reacts them. So what it's going to get left behind here is basically going to be your raw egg in the membrane. It's going to remove that shell. So day two, what you're going to do is you're going to take that egg out of here and you're going to transfer it into another container, and in the second day you're going to put this into some corn syrup. Now you don't want diet corn syrup or anything, you want the full-fledged corn syrup. And if you don't have corn syrup, honey will also work. You can also use a concentrated sugar solution. So just make like a saturated sugar solution and transfer that egg over into here. Now, any idea what happens to that egg when you put it into the corn syrup? Well, here's the egg right here. Think about osmosis now. We have a membrane that's going to surround this egg. Where is the solute more concentrated? Inside the egg or outside? Inside or outside? Outside. So what's going to happen to the water? It's going to go out where? Go out of the egg and into the corn syrup. So what's going to happen to the egg? It's going to shrivel up, exactly. So your egg is going to look kind of like a deflated football. They often hear it described. And that's because water is moving out of the egg. Well, then on day 3, what you can do is you can take that egg out of here and you can put it into some ordinary water. When you take that egg out and put it into ordinary water, what do you suppose happens to the egg? Right, water will move into the egg because where is the solute more concentrated at this point? Inside the egg. So it's more concentrated inside the egg, then water is going to move up into it, and actually very often it gets very large, and that's because the water molecules are moving into the egg, and that's how the osmotic pressure is acting. So if you want to talk about osmotic pressure, that's the water that's moving into the egg here. Here the osmotic pressure is pushing the water out of the egg into the corn syrup. And one of the reasons why I like doing this one is it illustrates very much. Now, how many are planning medical careers here? I know many of you are. So let's say that we want to administer a drug to someone. If we administer a drug to someone, we want to get that drug into the body. Let's say we want to put that drug into an IV bag, or IV solution. Okay, well, let's say that that IV bag just contained water. If that IV bag contained water and we start injecting that water into the body, that water is going to run into those cells, those red blood cells. What's going to happen to the cells? Well, they're going to be expanding and popping. And if it's too concentrated, what's going to happen is that every time that IV solution runs into your red blood cells, then your red blood cells are going to start shrinking. So when an IV is administered, no matter what drug it is, even if it's morphine, which is going to be something really dilute, that's always added to a solution of this isotonic with the blood plasma. And if it's a glucose solution, that solution is going to be 5.5% glucose. And if you add it to a saline solution, it's going to be 0.92%. And so those are very specific concentrations that are used because you want them to be isotonic with the blood plasma. You don't want the osmotic pressure causing the cells to swell or to shrink. You want them to maintain their same size. So that's one of the ways that this is used. But it's a fun, if you've never done it before, it's a really fun experiment and one that I'd recommend you giving a shot. Now another application of this is through what we call reverse osmosis. Anybody know what reverse osmosis is or what it's used for?
Do they use it for getting salt out of water to make drinking water?
Yes, it's a way to remove not just salt, but basically any impurities out of drinking water, actually to make drinking water. So a place where it's really common is in desalination processes. If you want to desalinate water, remove the saline from ocean water, you can use reverse osmosis, and that's the most effective way to wind up doing it. But if we consider what reverse osmosis is, let's say that we looked at a pipe. What this is a pipe that would be used to purify water, and in the center of this pipe we're going to put a membrane. So again, this right here is what we call a membrane filter. Now the way this works is that coming into here, and I'll put a different color here, let's use green. Coming into here is going to be your tap water, and coming out on this side is going to be your pure water. Now if you have tap water, on this side, and you have pure water over here, which direction is osmosis going to want to act? Is osmosis going to push the water that way, or is it going to push it this way? Think about this. Left or right? How many think it's going to, osmosis is going to push water to the left? Raise your hands. I think it's going to push to the right. Okay. Well, which side is the impure water? The tap water is impure. And so osmosis, water moves in the direction from lowest solute concentration to highest solute concentration. Which direction is the solute the highest? Yeah, it's on the tap, it's on the left. So that means osmosis is going to push it to the left. And that's how osmosis would act. But this is called reverse osmosis. It's called reverse osmosis because what we're doing is we want ultimately the water to wind up passing through this way here. And so in order to have this work, and I'll write this in here so we just have it, the osmotic pressure is going to be acting in this direction, but we want the water to come out the other direction. And so again, we call it reverse osmosis because we are pushing water opposite the direction that osmosis would want to take it. Now, how is reverse osmosis going to work? Well, what would have to be true about the line pressure, that is the pressure in the pipes, compared to the osmotic pressure? This line pressure would have to be greater than the osmotic pressure in order to push water through here. If the osmotic pressure is greater, you're never going to get water through. So you have to have a line pressure. You build water towers. That's why you got a water tower. It's going to put a whole big volume of water up there that as it sinks down is going to wind up pushing water through the lines. And sometimes you need to pressurize the lines a little bit more. I live out in the country and have a my own well, and my tank there that I use has to have a pressure that'd be large enough to wind up pushing it through. And if it's not, then we have to apply some additional pressure to get that to work.
So now, is this the same way that a water softener works?
Water softener works on a totally different principle. Water softener works on ion exchange. And basically, when you soften water, you still have ions in solution. The difference is that before you soften it, it has calcium ions in it, and magnesium and iron. When you soften it, you're replacing those calcium, magnesium, and iron ions with sodium ions. And the reason why we soften them that way is because, if you go back to our solubility table, sodium compounds are soluble. And so calcium compounds, when they combine with things like carbonates, which are in your water, and the carbonates just simply come from the carbon dioxide in the air, the carbonates that are in the ground, and so forth, and so that's what gives the hard water scale. And your sodium carbonate's not. So that's a different process. Many believe, though, that the reverse osmosis is our water purification system of the future. The big problem right now is, in order for osmosis to work, how large would these pores have to be on these membranes? Really big or really little? Really little, because they have to allow through water molecules, but they have to keep all the other ions back, like sodium. So even those things are very, very tiny. So what do you think happens to these filters? They clog very easily. And so the technology today that goes into reverse osmosis is going into how do we keep these membranes from clogging up, or realizing that they are going to clog up, how do we mass produce them and replace them in such a way that we don't interrupt the process of water purification. But reverse osmosis is the way, like when you desalinate, if you go out and go kayaking out in the ocean or whatever, you have a little pump there, and that basically what that pump does when you go through there is it create a pressure of that salty water, create enough of pressure that forces the water on through the membrane. Yes,
It's not taking like a tremendous amount of energy.
it does take a tremendous amount of energy, yes.
So like that's why we don't have like facilities on like the coasts that just produce pure water.
Exactly. And in the future, we're going to be running those things with solar and fuel cells that are hydrogen-based that don't wind up producing pollution.
Yeah.
Yeah. But yeah, that's tremendous amounts of energy go into that. Okay, anybody else? All right. Then we are going to have a very brief introduction here going on into chapter 13. And this stuff here, I have some demos that I brought in to do this. Chapter 13 deals with a topic called chemical kinetics. And right away when you look at this, you see the word kinetics. What comes to mind? Kinetic energy. And kinetic energy is the energy associated with what? Movement, exactly. So we're going to be talking about how molecules begin to move. And specifically when we talk about chemical kinetics, what we're looking at is the study of reaction rates and factors that affect reaction rates. So chemical kinetics is the study of reaction rates and factors that affect the rate of chemical reactions. And in the demo here today, I'm going to look at this reaction. I'm going to look at iron reacting with oxygen, and we're going to make this stuff here, which is called what? Iron oxide. Specifically, what type of iron oxide? Iron, not iron 2, iron 3. Remember, the Roman numeral comes from the charges. So we're making iron 3 oxide. And in case you've forgotten that, it's because we have Fe3 positive with O2 negative. And so it's iron 3 oxide because of the 3 positive charge here on the iron. So now, to do this, I have a number of things. First of all, I have an iron nail here, and we're going to go ahead and see if we can try to force the iron to react with oxygen. What's something we could do with this to, I mean, obviously this has been sitting here now. I found it on my cart and had this course 7 years ago. And so sitting here in 7 years, I do actually have some iron oxide on here right now. And what is iron oxide also known as? Rust, right. And so if you look at the tip of my nail, you're actually going to see a small amount of rust that's on here. Again, this has been 7 years. Where is it? Try it again. Here we go. But now, if I wanted to speed this up, where is it at? Here we go. You can see a small amount of rust on the very tip. What could I do to speed up the reaction of iron with oxygen? I could do what? All right, I could heat it up. So these would be some factors we'd look at that would affect the reaction rate. So factors affecting the rate of reaction. One of them could be temperature. And so we could either heat it or cool it. So let's go ahead and try to see what happens if I were to heat this. I'll take my nail and put it in the flame. And I guarantee you this is going to help, but you probably don't have enough time. So temperature alone in this case isn't going to do it. What else could we do to the iron? What else do you think would make it react faster? We could increase the oxygen. And because I knew you were going to say that, Sean, I just happened to bring with some oxygen in a vial here. And so we could take this nail, heat it up nice and hot. And because Mandy's right here, I need to move this over a little bit. So I'll go ahead and put this into the oxygen. That's not doing it. But increasing the concentration is one thing that we do often do to make things react faster. So we could change the concentration. Of course, if we increase the concentration, usually what happens? Reaction rates will tend to go up. They'll tend to increase. If we decrease the oxygen, I can't take that away. It's kind of hard for it to react, but sometimes there will be things where you decrease the concentration, it'll make it faster. Usually we have to increase it though. Now how about if I take this and grind it down? What am I changing if I do that? Yes?
Surface area.
Surface area, exactly. Surface area is one of the things we could change. Now I don't have anything to grind this down, but I do have some steel wool. I knew you were going to say something about that. So this is kind of where I need to move my stuff around just a little bit. So I think we're in good shape here. I'm going to move this out of the way. So I'm going to take some steel wool and we'll heat that up, if I can get it out of here. Nah, we're good. Okay, and we can see how that does help a lot. So we're basically increasing the amount of surface. And why is that going to work? Why is that going to work? Well, it's not so much with the bonds. If we increase the surface area, Charles? Exactly. We have a lot more surface or atoms exposed. So surface area really is only true if we're dealing with solid reactants, right? But now, one of the things I can do is I can combine some of these factors. I could actually take the steel wool and I could then put it into the oxygen and see what happens when we do this. And we see that it reacts very rapidly indeed. Okay, so sometimes we need to combine several different factors. In this case, we had to put all three of them together before we wound up finding one that did it fast enough for us to see. And then there's a fourth one that I don't have for this particular reaction, but a fourth way we can speed up a chemical reaction or change its rate is to use something called a catalyst. And we define a catalyst as a substance that speeds up a chemical reaction without being consumed. Now here's the time of truth. You've been lied to your entire life if you've been told that. Turns out that we've lied to you, that catalysts are in fact consumed, but what we find out is that they're actually regenerated in a later step of the experiment. So a catalyst usually does change to something else, but changes back to its original form. And what I'm going to do is I'm going to illustrate that by taking some hydrogen peroxide, and I'm going to put the hydrogen peroxide into this volumetric flask. And just on its own, this hydrogen peroxide will decompose, and when it does decompose, we're going to be over about 1 minute today, I apologize. When it does decompose, hydrogen peroxide will break down to yield water and oxygen gas. And so it looks something like this. And balancing it, whatever, right here. So this is something that is happening on its own right now, and it's one of the reasons why if you buy hydrogen peroxide in the store, why it has a shelf life, because even as it sits in there in the bottle, it is decomposing. But I want to speed up that decomposition a bit by adding a catalyst. Catalyst I'm going to add here is potassium iodide. Potassium iodide. And before I do this, you need to close your eyes, make a wish. Okay, you can open back up. And then I'm going to rub the bottle and grant you your wish. But did you notice what happened to the color in here? And what happened to the yellow? It disappeared. And the reason for that is because in the reaction, the catalyst, which was the potassium iodide, changed into something else, and at the end it changed back into its original state. Not its original state, but its original substance. And so, part of what we're going to do in this chapter here is we're going to talk about how catalysts work and talk about how it affects chemical reactions and their rates. So, any questions? All right. We will see you then on Thursday, unless you have me in lab tomorrow. Class visits. You don't have to dress in your Sunday best, but do try to look nice to represent ARCC.